Good evening and welcome to Monday Night Calculus. My name is Curtis Brown. I'm really excited to be joining you here yet again for another season of Monday night themed calculus events. I think this season is the first time we've been able to do them all on a Monday night. We don't have any different nights scheduled, and I think we even have all the same 2 weeks in between all the way through this whole season. So I'm very excited to be able to have a consistent schedule this fall. Of course, I'm joined again by Steve Kokoska and Tom Dick. Really excited to have you two guys here this evening. A couple of things before we get started. First of all, feel free to put whatever you need to in the chat in terms of questions and answers. Steve always has something to put me on the spot and ask me questions that I don't know the answer to. So I'm looking to the chat for help. So I'll be watching for that. Secondly, if there's any students out there, of course, please ask questions. Do the call outs that you need to your teachers so you get the extra credit that they potentially promised you. And really excited to have this evening. So without further ado, Steve.
All right. Thank you very much, Curtis. I'm going to try to share my screen there. How about that? Can you see that?
Looks great.
Well, it's wonderful to be back with you and Tom again this season. I was kind of expecting the Peyton brothers to be with us tonight, but maybe next time. That would be good.
Yeah, they turned me down when I talked to them earlier.
I can't imagine why. I want to remind everybody again that this is supposed to be kind of interactive. So if you have any questions, please feel free to ask. And if you have any problems that you'd like Tom and I to address, please send them to Curtis. And any technology questions, sure, that we'll be happy to take a look at also. So tonight we're going to take a look at limits, numerical, graphical, and algebraic approaches. We've got lots of good problems and lots of good technology. These problems have been posted at least a week in advance, so I hope you've had a little bit of time to take a look at these. We'll show you some of our answers, and maybe you have some questions about how we solve things. Here we go. So we're going to start out by taking a look at a table of values to estimate the value of some of these limits. And I'm going to start out by underlining a word here. We are indeed just estimating right now. These are in no way proofs just by taking a look at a table or by taking a look at a graph, but they often give us a good idea about what the real value of the limit is. So let's try this one here. The limit as x goes to 0 from the right of x squared times the log of x. And I'm going to think out loud a little bit about this one off to the side first. I see a product of two functions, and as x goes to 0 from the right, I notice that x squared is going to 0. Okay, that's pretty easy. And as x is going to 0 from the right, I think a little bit about what the log function does, and that's going to minus infinity. And so I don't really know what this product is doing. These two functions in my mind are sort of competing. If x squared is going to 0 in my mind faster than whatever the log x is doing, then it's going to drive the product to 0. If the log x is going to minus infinity faster than x squared, then it's going to drive the product to, well, minus infinity. And on the other hand, there could be some sort of compromise. Maybe this product is going to some number in between. So the first thing I did was try to take a look at this with a table of values. And I started at 1.1 and went to 1 and then closer and closer to 0 from the right-hand side. And if you take a look at these values, one interesting thing here I stumbled across was, I didn't realize this at first, is that this function actually is positive for a while here and crosses over the x-axis. And then it seems to be getting closer and closer to 0. As x gets closer and closer to 0. And there's sort of some graphical support for this. I'm going to show you some graphs with that I've created with Mathematica. Tom and Curtis know I enjoy using that software. But Tom will, of course, show you how to produce some of these graphs and tables using technology. So this is what the graph looks like. The domain here is x greater than 0, and it's kind of hard to see. But there is an open circle right there at the origin. And I'm pretty convinced when I produce this graph when I produce this table, then in fact, this limit looks like it's 0. Now, again, this isn't a proof. This isn't exact, but this table and this graph sort of suggests this. That's a good one to start off with. I like that one. Some open questions here that students might think about, teachers you might ask your students about, where does this cross the x-axis and why? And what's happening to this as x increases without bound? Does the product increase without bound? Does it come back around here? Does it come back down to the x-axis at all? Something to think about. All right, as you might be able to tell, I'm using some new technology tonight, so I'm a little funky with this, but I'm going to try here. Let's see if we can get to part B. Hey, how about that at work? So let's take a look at the limit of this composition function, the limit as x goes to 0 from the right of the log of the sine of x. Now, I probably shouldn't do it this way, but I'm going to try to argue a little bit before I look at the table and before I look at the graph. And I'm going to do it down here in the bottom right-hand side. I've got a little bit more room here. Let's see, as x goes to 0 from the right, what is the sine of x doing? Let's see, I've got to think a little bit about my trigonometry. Maybe think a little bit about the unit circle. Maybe think a little bit about the graph of the sine of x. What is that doing? Well, that's going to 0 also. And I might think a little bit about how. Think about that graph of the sine of x. That's actually going to 0 from the right also. So if this argument is going to 0 from the right, then okay, I know what the log function looks like. So I feel comfortable in thinking about that going off to minus infinity, that composition going off to minus infinity. So let's see if the table of values supports that, if the graph supports that. So here's my table of values, and as I get closer and closer to 0 from the right, these are values of this original composition function, not just the sine function or anything like that, the composition. And that does indeed look like it's decreasing without bound, although even for what is it, 0.000001, it's only minus 13. So I guess I've got to get really close to 0 to see that really decreasing without bound. But there is some numerical evidence, and I graphed this, and it does indeed look like it is decreasing without bound, going off to minus infinity. There's some numerical evidence, some graphical evidence. Some open questions again. I wonder what this graph is doing out here as x increases without bound. Does it cross the x-axis? Does it come back down again? Is there a vertical asymptote in there somewhere to the right of 0? Something to think about. I'm going to try one more, and then I'll hand it over to Tom for a little bit of technology. Let's take a look at this one. I like this one. And I'm going to try to do some arguing about this one too before I look at the table and the graph. So this is the limit as x goes to 0 from the right. And I apologize, I don't mean to imply that all of these limits are x going to 0 from the right, but these were some good ones that I found. As x goes to 0 from the right, let me scribble a little bit down below. As x goes to 0 from the right, what's 1 over x doing? Well, the denominator there is getting very, very small positive. And so that's driving that expression, that quotient, let's see, to plus infinity. As x goes to 0 from the right, well, we've seen this a couple of times already. What's the log of x doing? Well, that's going to minus infinity. So now let's think about this difference. If this expression is going to plus infinity, increasing without bound, this expression is decreasing without bound, but wait a minute, there's a minus sign in there. It kind of looks like that difference should be increasing without bound. And in fact, that's what this table suggests. As I get closer and closer to 0, boy, the values of that difference are getting very large quickly. And there's a graph of this function to the right of 0, and it does indeed look like this limit as x goes to 0 from the right is equal to plus infinity. Here's another couple, or at least one more thing that teachers, you might investigate, students, you might think about. What if I change this just slightly and make that a plus sign? I wonder what that limit is there. Cool. Tom, can I hand it over to you for a little technology?
Sure, I'll give it a shot.
All right, here we go. All yours.
Okay. I'm gonna share my screen. Let's see. Okay. Okay. So I'm going to look at these problems that Steve just analyzed on the TI-84, just basically kind of looking at how you can use the technology to do exactly the kinds of investigations that Steve talked about. And I would call them investigations. Steve was careful to say these are ways to kind of estimate a limit. They're definitely not proofs of limits, but they really do give you a good idea of what's going on. So I'm here on the 84, and I'm just going to go to the y equals menu. And Curtis and Steve, is that showing up okay, the 84 screen?
Yep.
Okay, great. All right, so we'll just go to the y equals screen here. And I'm going to enter into y1, the function, that first function that Steve looked at. I think that was x squared.
Hey, as you're doing this, Tom,
Yes.
and typing this in, Steve, I want you to be thinking about a question that's come up a couple of times in the chat, which is how you might reason about that challenge question you just posed to everybody, where you change that subtraction sign to a plus sign. Maybe would you think about common denominators, that kind of thing. So think about how you're going to respond to that.
Okay.
And maybe Tom even has a trick up his sleeve of how he could look at that on the calculator.
Let's see. All right, so this is, I think that first function was x squared times natural log of x. And we could certainly just do a graph of this. I'll do that with just a regular Zoom decimal window, I think. So this would be kind of a standard graph there. And this looks quite a bit different than Steve's graph. And that's because Steve's window was really a much smaller part of my window. And so we could zoom in on this if we wanted to take a look at this limit in a window similar to Steve. So we're already there at the origin, and we were approaching 0 from the right. Okay, and so this is starting to look a little bit more like Steve's graph. And it looks like graphically, as x's approach 0 from the right, it looks like we're approaching 0 in the y values. Now you may be looking at this and thinking, oh, wait a second, is this saying that the value at x equals 0 is actually 0? Because natural log of 0 is not defined. But just want to point out that this is just giving me the coordinates of my cursor there. And it's not actually on the function graph. If we actually want to look at a point on the function graph, we need to pull up trace. So I'm going to pull up the trace. And notice that when I actually get onto the function graph, I was still on x equals 0, but notice that there is no y value there. Okay, so there really is, I think Steve had it depicted as like an open dot on his graph, and that would be the correct way to signify this. As soon as I trace over to the right just a little bit, now we're getting a function value. So this function is defined for all values x greater than 0, right at x equals 0, it's undefined. That's why that limit question is kind of interesting. Are the values of the function approaching some definite value as we get closer and closer to 0? Now, this is the graphical view, but I think the looking at the numbers is really illuminating too. So let's look at how we might use the table feature here. So I'm going to, we've got that already stored in Y1. I'm just going to pull up the table. That's the shift or the second function of graph. You can see table up there on my keyboard. And this is coming up with, lots of interesting values. I think this is probably the default for the table setting. It starts out at x equals 0, and you can see that it's just incrementing by 1 for my x values. And then for y1, let's see, y1 of 0, we get an error. Well, that makes sense because we just talked about how the function wasn't even defined there. But believe it or not, when I've worked with students, sometimes they're looking at this table and trying to make sense out of it, but this is not a very good table for the question we have at hand. We're interested in what's the behavior of the function values as the x values get closer and closer to 0 through positive values, x approaching 0 plus is that notation. And so we need values of x that are getting closer and closer to 0 through positive numbers. Now, I could try to generate those, but really, I think at this stage of the game, it's just as easy enough to go to the table set. That's going to be the second shift of window. It's a nice analog. Window is to graph, as table set is to table. So we go to table set, and you can see the table started at 0, x equals 0. The delta table is the increment. But really what I'm going to do is rather than play with those, I'm just going to go down to the independent variable and cursor over to ask. And that's where I can just put in values of my choosing. Okay, so let's hit enter on that. And now let's go back to the table. So second shift, right? Now I've just got a blank table here. And now I want to be thinking about, okay, what if x is approaching 0 through positive numbers, let's look at some values that are getting closer and closer to 0 in that sense. So I might try right off the bat, how about 0.1, 1/10. We'll enter that. I get negative 0.023. Okay. Now I could say, well, let's get closer to 0. How about 0.01? Excuse me, yeah, 0.1. So that's 100. Wow, okay, it's already, I have to learn how to read that, right? -5, e -4 really means it's -5 times 10 to the -4. So that's already getting very close to 0. And then I'll put just one more, about 0.001 after the decimal point. Boom, there it is. So it really getting the sense these numbers are negative, but they're getting very, very close to 0 themselves. So it's looking like the function values are approaching 0 as x approaches 0 from the right. Now, if I go back to y equals, it's kind of interesting if I go ahead and enter one of those other functions. Somehow I jumped all the way down. Okay, let's see. There we go, y2. Another one of the functions Steve had was natural log of the sine of x. Close off my parentheses. And I'm just going to go straight to the table this time. And if I do that, boom. Notice those values that I had already entered, they're still there. So this actually, it's kind of lucky in the sense that both of these limits were as x approaches 0 from the right. So I didn't, these are still going to be good values for x for me to check out. These are, they're negative. They seem to be decreasing, but not super fast. So that's interesting. So I might go down here and ask for a value a lot closer to 0. So like, how about 0.000? Let's put in a lot of zeros, shall we? How about that? 1, 2,
I
3,
did up to 21 zeros while I was playing with this one.
Oh, you did? Okay. So here, that point, this would be what, 1 times 10 to the -8, something like that. Counted it right. Wow. Okay, so we do get the sense that this is decreasing and it's keeping decreasing, but Steve, I don't know how you feel about it, but this thing's decreasing very slowly.
Sure is.
And what'd you get, Curtis, when you put in 21 zeros?
I think it got up to, I don't know, 90 or something like that.
Negative 90? Okay,
Negative
so
90, something like
it's
that.
definitely, and this is a place where I think maybe the graphical view is a
Yeah.
little more convincing that that thing is acting like a vertical
So
asymptote.
for sure. I have two comments here, Steve. One that Miss Connolly put in the chat, which was if you arrow to the right and get up to one of those values where you've got the exponential numerical display there, -2e to the -15. You can actually get the decimal equivalent show down below, so you can kind of see that in a maybe a little bit more expanded form. So that's helpful, especially on those ones where it's, you know, -7e to the -6. It'll actually show the full decimal there on that one. The second
Wonderful comment, and that's exactly right, especially for these where it's had to use the exponential notation. This
Yeah.
is giving us a lot more detail about what
Yep.
that looks like.
So then the second comment I have is rather than going back to Y1 or Y2 or whatever to edit, if you see the across the top there where it says press up arrow to edit the function, if you up arrow all the way up to the top there, and you get up onto Y1, you can now press enter to edit that function right here on this screen and update live. So for example, if you were interested in evaluating part C from Steve's questions there, where we've got the what was it? The natural log, or 1 over, what was it? 1 over x minus the natural log of x. I think was what it was. Isn't that the third problem?
Was 1 over x minus log x.
Yeah, 1 over x minus log x. So you can just type that in right there on top of y1 there. You'll have to delete that. Well, you'll need to delete that math template, I think. There you go.
Delete that also.
Yeah, I think that's good. There you go.
Oops. Okay. Didn't like
That's
that.
all right. Just do minus log x. And now you've got that entered in there and it'll evaluate at all of those same inputs.
Okay, so I'll have to hit enter and boom, there we go. Okay.
Yep.
And this one now we're really getting that feeling that, wow, that one is taking off. So it's
It just
growing
takes off.
pretty fast, which made a lot of sense. As Steve analyzed, you actually had that first term was going to positive infinity, and then you were subtracting a term that was going to negative infinity. So that's doubling it up almost. Actually, doubling up, I really shouldn't use that term because I think those things are probably going to their respective infinities at different speeds, which is part of the challenge question, I think.
Yeah.
All right. So I think the table feature is really nice. Let me show you one other thing you could consider doing. I'm going to go back to y equals. And to illustrate this, I'll tell you what, so you see the y1 has been updated there.
Mhm.
I'm going to go ahead and turn that deselected. Oops, I arrowed over too far. Okay, let's see. Excuse me, I'm fumbling around here a little bit. Okay, what I'm trying to do is just get on my equal sign there, turn that off. Didn't quite do it. All right. One more try. There we go. Okay. If you wanted to generate some x values rather than using that ask function, another thing you can try is the following, is I'm going to make y free. I'm going to look still at that y2. So it's natural log of the sine of x. What I'm going to do is I'm going to make y3 equal to y2. So I went into my variables, I'm picking up y2. And I'm going to evaluate y2 at 10 to the negative x power. Okay, so let me enter that. Now, here's what I want to point out is that now if I set up my table like I would normally, where x is 0, 1, 2, 3, 4, and so on, notice that 10 to the minus x is going to be like, okay, 10 to the 0, that's 1, 10 to the minus 1, 10 to the minus 2, 10 to the minus 3. It's getting closer and closer to 0.
Oh
through
my
positive
goodness.
numbers. So it's
That's
set up a
genius.
nice table for me. So I'm going to go back to table set. And I'm going to go and put it back on auto again. That's where it'll automatically fill in the x values starting at 0 and incrementing by 1. But remember that with y3, what I've got in there is 10 to the minus x. So now when I go to the table, these y3 values, okay, these are actually corresponding to 10 to the power, 10 to the negative power you see over here. Now you got to be careful with this because you got to create exactly what it is you're looking at.
Yeah.
So, but this is in some sense, as x increases here, the value that's being inputted in the y3 is getting closer and closer to 0 through positive numbers. And you can do that game with any target value. So if x is approaching, say, 7, you could say, okay, I'm going to make y3 equal to y2 of 7 plus 10 to the negative x. And then if you want to approach from the left, you could have 7 minus 10 to the negative x. That way, those values will be closing in on 7 from either direction. All right. Okay, I'm going to shut up there and turn this back
Tom,
over.
I learned something new today. That's a new strategy I've never seen before. While you're switching over, Steve, did you come up with a solution about what I asked you, by the way?
Well, I got a possibility anyway. All right.
All right.
I got something to think about, something you can think about. All right.
Okay, I've stopped share. Okay, there we go.
Here we go. All right, so down on the bottom left-hand side, I think the question I asked about is what would happen if we put that, made that 1 over x plus the log of x. So I apologize for this, Curtis, but a little bit more scribbling. As x goes to 0 from the right, this expression here, let's see, that's going to what? Plus infinity. And this expression, the log of x, is going to minus infinity. So it kind of looks like really big number plus a really small number in magnitude, very big negative. So it looks like they might cancel out. You might get closer to 0. So what do you do here? If you don't have a table of values, how can we argue on this one? Well, there's probably a better way to do this, but here is a way. Here's something to think about. What I did is I just took this expression and got a common denominator of x. And I thought about the numerator a little bit. So I need to know, what is this expression doing as x gets closer and closer to 0 from the right-hand side? Well, that's one that's very, very similar to one we just looked at, isn't it? We looked at part A this evening, which was x squared times the log of x.
Mm-hmm.
So it's very similar. So we could take a look at that circled expression product right there and try to figure out what that's doing. So here's a hint. I think that's going to 0. So if that's true, then as x goes to 0, that expression looks like 1 plus something very, very small divided by small positives. So the numerator is getting closer and closer to 1. The denominator is getting very, very small positive. And I'm guessing that that drives that whole expression to plus infinity. Now, this is really interesting because that's more evidence to suggest that, you know what, the log of x really grows very slowly. Even as it's going off to minus infinity, this says that the 1 over x is really dominating and driving that whole expression to plus infinity.
Yeah, the rate of change of the natural log function is
Slow.
really slow. And that question kind of investigates that significantly.
It does.
That's cool.
It does in an odd way. Yes, it does. It does. All right, good question. Excellent one. All right, I got a couple of questions to deal with these two graphs, and I'm not exactly sure why, but I've seen a number of questions like this appear recently in the AP Calculus Facebook group. And in fact, we're introducing a new feature tonight. I don't know if we're going to get to it, but we have what we're going to call overtime problems. So these are problems that after we have posted our problems, Tom and I have seen on the Facebook page, we thought, you know what, that might be a nice one to look at. Even if someone has already provided a solution, it might be nice to look at a little bit more detail and maybe even with technology. So I've seen a number of problems like this, and you know what, they're very clever. They're very good problems, and they force us to think about limit properties and when can we use these limit properties. I'm not sure that I've seen one like this on a free response question ever. I'm going to guess that you might see one on a multiple choice question on the multiple choice portion of the exam, but these are clever. So I have two functions, f and g. I'm not going to give you an analytical expression for f or g, but I'm giving you the two graphs up there. You can see that they're both discontinuous. And I want to see if the following limits exist. If they do, I want to see if I can find a value. And if they don't exist, I want to state that, figure out why. So the first thing I want to look at is the limit as x goes to 1 of f of x times g of x. I'm going to try to get all of this on the page if I can. There we go. So here's my natural, I think, instinctive, intuitive way to answer this problem. I have a limit of a product. And I think the intuitive thing to do is to immediately break that up into the product of the limits. Now you'll notice that when I did that here, Curtis, I have a question mark above that equal sign. And I put it there to remind you, you know, you can't always do this. We do it sort of instinctively, but you can't always do this. Let's take a look at these two limits on the right-hand side for a second. What happens as x goes to 1 of f of x? Well, let's see. If I'm looking at this graph up here of y equal f of x, as I approach 1 from the left and 1 from the right, the function is zeroing in on two different values. So this limit, in fact, does not exist. Let's take a look at, just for the heck of it, as x goes to 1 of g of x. This one, let's see. As x goes to 1 of g of x, well, there's an open circle there at 1. There's a solid dot down here. A common error that we see on the AP exam is some students would say that that limit is -2. That's not true. Remember, as we take a look at a limit, we want to know what is the function zeroing in on, not what is the value there, but what is it getting closer and closer to? And this one sure looks like 0. Okay. So I think the intuitive thing to do, the instinctive thing to do is to say, well, since one of the limits on the right-hand side doesn't exist, then this overall limit, this product doesn't exist also. But not so fast. You can only use this property if the limits on the right-hand side exist. One of them doesn't exist, so all bets are off. You cannot apply this property of limits. So what do you do here? So what we need to do is to actually take a look at one-sided limits. And don't let me make a mistake here, Curtis, there's lots of notation. The limit as x goes to 1 from the left-hand side, we'll split that up, and I can do this. These two one-sided limits exist, so let's see. As x goes to 1 from the left-hand side of f, let's see, that limit is -2. As x goes to 1 from the left-hand side, well, that limit is 0. So the product, that's going to 0. Got that. As x goes to 1 from the right-hand side, what's f doing this time? Well, this time f is zeroing in on, well, it's equal to 3 all the time over there. And as x goes to 1 from the right-hand side, over here of g, that's still approaching 0. And so the product is 0. So now I'm going to employ another property or theorem about limits. The limit from the left and the limit from the right are the same, 0. And that means that this overall limit exists and is equal to that value, 0. So the gut reaction up here is not quite right. We cannot apply that property of limits. And to solve this problem, we need to take a look at one-sided limits. I like that one. That's a cool problem. Let's try another.
I got that one right, Steve.
Okay. I don't mean to sound surprised. I'm sorry.
Come on, man.
All right, let's take a look at this one. Similar in a sense, this one is a composition of functions. The limit as x goes to 2 of f of g of x. So let's see here. Well, what's g of x? What's that inner function doing as x approaches 2? As x approaches 2, let's see, what's g doing? Well, as I come in from the right, as I come in from the left, g gets closer and closer to 1. So this inner function here is getting closer and closer to 1. And so just sort of thinking out loud, that kind of looks like that, well, as I get closer and closer to 1 here with f, that limit doesn't exist. And so my gut reaction is, well, the limit of this composition function does not exist. But wait a minute. What's the rule here? What's the property about the limit of a composition of functions? We have to think about that a little bit. If the limit of the inside function exists, when can you apply this? When can you just take f of that value? Well, the function f must be continuous in order for that to work, and it is not continuous at that limit of g, which is 1. So there's no property, there's no theorem here that I can really apply here, even though my gut feeling says, well, the limit doesn't exist. I've got to take a look again at one-sided limits. So let's see, what happens as x approaches 2 from the left-hand side? As x approaches 2 from the left-hand side, what's happening to g? Well, it's getting closer and closer to 1. How? From the left, right? It's coming up like this, so it's approaching 1 from smaller values. So it's approaching 1 from the left-hand side. And I like to do this as a separate limit problem or a separate limit statement. I know what that inner function is doing now, so I'm going to use another variable. T is approaching 1 from the left. What's f of t doing? Well, that's approaching -2. I can see that in the graph. In fact, it's equal to -2 to the left of 1. Cool. As x approaches 2 from the right-hand side, similarly, g is approaching 1 once again from the left, so I can write a similar limit here. It's approaching -2 once again, and so that overall limit is -2. That's a neat problem. That's a very cool problem where your gut might say, you know what, the limit doesn't exist, but in order to solve that one, I need to take a look at 2 one-sided limits. I'm going to try one more here. Curtis, did you get that one?
No, I went with my gut. I didn't think about that one all the way through. I said did not exist.
All right, well, let's try this one.
But I did get the last one right, it looks like.
Okay. You're going to have to send me that homework for verification. The limit as x goes to 2 of g of x, again a composition. Let's see if we can figure this one out. Let's see. What happens as x goes to 2? What's happening to g? Oh, well, we've taken a look at this one already, haven't we? As x goes to 2, let's see, from both sides, g is approaching 1 from the left. So, okay, I'm going to sort of reduce this. I know what the inner function is doing, so I'm going to use another variable here. T is approaching 1 from the left of g of t. And what's happening is now as I approach 1 from the left, g is approaching 0. That's a neat problem also. I like that one. Good. So again, I've seen several problems like this. One of the overtime problems has a couple of other questions about this. Tom, shall I take a look at one more here? Shall I take a look at number 3 before we try some more technology?
Sure.
Okay. Okay. Let's try 3 here. If I can work this arrow up just a little bit, if I can. Hey, how about that? Okay. So here's another nice limit. The limit as t goes to 0, 1 over t minus 1 over t squared plus t. Holy Toledo. As t goes to 0, what the heck? Just think about this a little bit. What is that expression doing? Well, let's see. I get 2 different values, don't I? As t approaches 0 from the left and from the right, the denominator would be getting small positive or small negative. And I guess in the other one, I'd have to think about this other expression and split that up as t times t plus 1. As t approaches 0, well, that's going to 1. And again, as I approach 0 from the left or the right, I'd be getting small positive or small negative. So that would be going to plus or minus infinity. Holy Toledo, I have no idea what this one is doing. I'd have to sit down maybe and take a look at one-sided limits. Let's see if there's an easier way to solve this one. So my approach to try to solve this one analytically, algebraically, would be to try to get a common denominator. And I see a common denominator would be the product of these 2 denominators. There's an easier one, of course. Okay, there's an easier one because I can write this as t times t plus 1. So there's an easier one, but I just did the quick gut reaction to this one, was I multiplied the 2 denominators together. So let's see, I think I get a t squared plus t minus t up there in the numerator, product of the 2 denominators. If I've done everything correctly, these 2 cancel out. I'm left with a t squared over t squared. Those cancel out. And this is really cool. I'm left with an expression which is exactly equal to the expression that I started out with, except that t equals 0. So if I want to find out what that original expression is doing at 0, I can ask, what is this new expression doing at 0? And this is an easy one because I can get the answer by direct substitution, and I get a value of 1, and that's pretty cool. Didn't look like that at all. I had lots of infinities and minus infinities floating around there. But in fact, this value is 1. And I didn't believe that at first, so I produced a graph here. There's an open circle at x equals 0, at 0, 1. And I believe that's what the graph of this expression looks like. It looks to me like there's a vertical asymptote at x equal minus 1. But that's kind of a nice problem that I solved algebraically. Let me take a look at one more algebraically, and then maybe I'll hand it over to Tom. This is kind of a nice one also. The limit as x goes to 0 of x divided by the square root of 1 plus 3x minus 1. You know, one of the first things I think we all try to do is to plug in an x equals 0. I think we all sort of intuitively try direct substitution quickly. If we do that, we get a 0 in the numerator. If we plug in a 0 in the denominator, we get a square root of 1 minus 1. We get a 0 in the denominator. So at least before L'Hopital's rule, that's a signal to me that I need to do something. I don't know if I can argue on this one, so I'm going to try something algebraic. This is kind of a weird thing because I'm going to try to multiply by 1 in a convenient form. So I'm going to kind of rationalize the denominator, which is kind of backwards. We don't do that, I think, often. So I'm going to multiply by 1 in a convenient form. I'm going to multiply by this expression right here, the conjugate of that expression in the denominator. I'm going to do that so that I can get rid of that square root symbol. So I have the difference of 2 squares down there in the denominator, and if I've done everything correctly, I get a 1 plus 3x minus 1. The 1s are going to cancel. I'm left with this expression. I can now cancel out my x's. And now I'm left with an expression, again, very similar to the one that we started out with, except that in this expression, I can plug in an x equals 0. I can use direct substitution on this limit. And I think if I did everything correctly, I get I get a limit of 2/3. I graph this one too down at the bottom. I guess you can see part of that. Let me see if I can arrow up just a little bit. Well, maybe not. There we go. And there is an open circle again above x equals 0. And while we're here, Tom, just before I hand this over to you, 2 things to think about in this problem. You'll notice that it seems like on my graph that there's nothing to the left of around an x equal, I don't know, minus 1/3. So one thing you might think about, what is the domain of my original function? This one right up here. And another thing you might think about, I know that the AP Calculus exam is still way off in the future in May, a long time away. But one thing I'd like you to teach is to impress upon your students is that when you solve a problem like this, if you have not executed, if you have not done the limit, make sure that you carry that limit symbol, that limit expression all the way down with you. We see this a lot, and I understand under the pressure of a high stakes exam, I get it, that sometimes students drop that. But you know, we're really stressing notational fluency, good notation, good communication skills. Make sure your students carry down that limit. Cool, Tom, you want to try a little technology on this one?
Sure. And in fact, what I might do, Steve, is rewind a bit to your number 2.
Okay, good.
And before you stop sharing.
Oh, I'm sorry.
That's okay. That's okay. I'll go ahead and take it.
I'll do it again if you want. Okay, you
No,
got
that's
it?
all right. Because
Okay.
I can create them again
Okay.
very easily. What I'm going to do is just pull up the TI-84 again. And I hope that's coming up.
Yes, sir.
So, Steve, you did this really nice analysis of those 2 graphically presented functions. In number 2, they were one of them was like piecewise constant, and the other one had they had interesting holes and sharp corners in them. It's sometimes really cool to take a look at those with the technology, though. To do that, we need to actually enter them analytically, enter them algebraically. Because they're piecewise, I know sometimes people say, well, can you really do a piecewise function on the technology? And the answer is, yeah, you can, and it's actually not hard to do. So that's just something I wanted to demonstrate here. So I'm going back to the y equals menu. And what I've done is I've actually got one of these already entered. This is the more complicated one, the Y2. And I'll show a graph of it in a little bit. But I just wanted to show with Y1, though, I'm going to enter the first one from scratch so we can see how that's done in case people weren't aware of how you can do a piecewise function. So I'm going to go to the math menu. And we see all kinds of things under, I'm in the math submenu of the math menu. I'm just going to scroll down all the way and we see Fmin, Fmax, numerical derivative. There's a definite integral function. If I keep going, there's a summation, log to other bases. There's the one I want. It says piecewise. That's exactly the one I want. So I'm going to hit enter on that. It says, well, how many pieces do you have? The default here is 3, but I can move that up or down. I think that first function you had, it was actually piecewise constant. It had a break in it.
Correct.
So and it was just in 2 pieces. So I'm going to hit my left arrow key to go down to 2 pieces. And I'm going to say, okay. And it brings up this nice little template for me where I can put in the 2 pieces of the formula. And to the right of that semicolon is what's the part of the domain that's good for. Now, I believe your function was equal to -2 for, now I have the benefit, I'm looking at this on a piece of paper, your actual graph there. Let's see, let me get over to, there we go. Now that domain was good for, I think, x's that were less than or equal to 1. So I'm going to go to the second shift of the math menu. It says test. Yeah, I see all those inequalities. I'll go into conditions. And notice it has an x less than or equal is that first one. You see a lot of, there's some compound inequalities here for specifying pieces of domain. I'm just going to enter that first one. And this is good for x less than or equal to 1. So this function will only, it'll evaluate to be -2, but only for these x values. Now let's do the other piece. Okay, then it jumped up to, oh wow, sorry, I jumped way too far. I think my issue is I'm holding down on my mouse too hard or something. So let's see, I think it jumped up to the value 3.
Yep.
And this was for all the rest of the values. In other words, all the x is greater than 1. So I'll go back to the second shift of math to the test menu, go over to conditions, and number 4 is x greater than, let me hit enter there. So x greater than 1. And let me just go down to y2 now, just to show folks. Oh, boy. Let me get inside of that formula. There. Okay, so when I get actually inside of it, you can see there's 4 pieces to it. It was a line that actually, now I had to figure out what the equation of that line was, but it looked like the piece of the graph of y equals x minus 1 when x was less than 1. Then it suddenly jumped down to -2 when x was exactly 1. Then it picked up again. And it was, oh, I think I need to edit this. Oh, I'm glad I did this. It should be a minus there. It was x minus 1 again, between 1, x is 1 and x is 2. And finally, for the last piece, it suddenly went down in slope. It looked like the line y equals 3 minus x. And that was for x greater than or equal to 2. Okay, so I'm going to enter that and graph them. Let me go to a zoom decimal window. And there's those 2 graphs. Now they're superimposed on each other. You had them as separate graphs. Something I want to note to people, this red graph was that one that had the hole in it. And it jumped down to -2. And if you look down here, I don't know if you can see it, there's a little red dot there. So that is part of that red graph. And so these are those 2 functions. And now what's neat is now that I have those analytically put in there, I could go back to y equals and now look at combinations of these 2 functions using arithmetic or composition. So for example, y3, I could look at y2 times y1, or y1 times y2, because you were looking at a limit of f of x times g of x. Okay,
Right.
so let's do that. So I'm going to do y3 will be y1 times y2. And now I'm going to graph that. And we were interested with this function. I believe we were interested in what happens as x approaches 1. Is that right?
Mhm.
Okay. Okay, so let's graph it.
Yes, as x approaches 1.
And you came up, your analysis was that it would actually have a limit of 0, I think.
Correct.
In this graph here, notice that it's coming down. And it's heading right, at x equal 1 is heading towards 0 from as x approaches 1 from the left. And as x approaches 1 from the right. Do you notice anything up here?
I see a black dot.
Yes, right at x equal 1, I'm getting 4. And if you evaluate the product of the values of those two functions, exactly at 1 is -2 and -2. Multiply those together, you get 4. So it's actually giving me this graph. So it's kind of cool. So you can really do this. I'm not suggesting this is the way to approach this on an exam, is to actually analytically find these piecewise functions.
Right.
On an exam, you're really going to be analyzing like you did, thinking through, okay, what's happening here graphically. But I think for instruction for teachers, this may be worth the effort to actually put these in analytically, because you can do some what if questions and then actually kind of verify graphically whether or not it makes sense. So, all right, I will quit the share there and turn it back to you. I hope. Let's see.
Let's see if we can do this again here, Curtis. Here we go. All right, in the interest of time, Curtis, can I just make a couple of comments here about some problems? And I did want to get to one of the overtime problems. I wanted to make sure that we told people about this problem number 4, because this is similar to, not exactly, but this is similar to one of the problems that was on the AP Calc exam this year. There was one of the parts had a limit question that was like this. It asked, here's a graph of a function f, and there are straight line segments, and then part of it between 0 and 1 is y equal x cubed. And we're asked about this limit, the limit as x goes to 1 from the left of f of x minus f of 1 over x minus 1. So I guess I'll leave this for you to think about a little bit. There are a couple of different ways that one might solve this. I think the expectation or the hope of the development committee when they wrote the problem like this was that students would see that and recognize that limit expression as a derivative. However, there are some other ways to solve this problem, and students solved this in a couple of different ways and did it correctly. But I think this is a good one for you to look at, especially since there was a problem like this on the exam, like very similar to this. All right, in our overtime problems, I want to give credit to Tony Record. There was a problem that someone asked Tony about. This was from one of his problems, and I made this a lot bigger. I introduced another graph over here of G, and I asked a lot of similar problems. For example, the limit as x goes to 2 from the right of f of minus f of x. That's a good one that you can look at. And by the way, Curtis, we are indeed posting these solutions, I believe, so that teachers can take a look at these. Here's another one, the limit of a sum using these two graphs. Again, an issue of, well, can I really apply this property of limits, or do I need to look at one-sided limits? A limit of a product. And I think I had another one in there, didn't I? Yeah, there's an interesting one. It's kind of a composition, but it's g of f of x minus 1. So you might want to try that one. And then finally, there was a second one, and I'm delighted that somebody sent this one in. This is kind of a cool problem, and we really don't have time to solve all of this, but I'll give you some hints about how I attacked it anyway. Here's a function g defined by this product. It's a rational function times the log of a rational function. And at what values of x does the graph of g have a vertical asymptote? Well, I did a little bit more with this. And one of the first things I thought about when I looked at this problem is I'd want to know, well, what's the domain of this function g? And so the first thing I looked at, I believe, was the argument of the log. And I know that that argument must be greater than 0. And so I did a little bit of simplification in there. And when I did all of that, I realized that x has to be greater than -3, strictly greater than -3. We can't have that argument being equal to 0. It has to be bigger than -3. But now, in addition to that, we can't have x equal to 0, because if x is equal to 0, we get a 0 in the denominator there. And we can't have x equal to 5, because we get a 0 in the denominator there. So, all right, I'm thinking out loud. I now know what the domain is. It's x greater than -3, but x can't be 0 and x can't be equal to 5. Curtis, I feel obligated to ask you one question for tonight. So where does that suggest we might look for vertical asymptotes?
Seems like you ought to look at 0, 3, and 5.
0, -3, and
-3. I apologize. -3.
Exactly right. I think
and -3 from the positive side, right? Because since
Absolutely.
it can't be equal, it also can't be less than. And yeah, so
Absolutely. I think that's correct. And there's some really surprising results on this one. So I would encourage you to take a look at these limits. I'll give you a little bit of a hint here down at the bottom. I think I included a graph. This is what I got. It turns out, I believe,
really
that
interesting problem
for this function, yeah, this is a real cool one. It turns out that there is a vertical asymptote, I believe, at x equal -3. There's a vertical asymptote at x equals 0. But at x equal 5, it's kind of hard to see, but I think you can see it on my graph. At x equal 5, remember, the function is not defined there, but there's actually just an open circle, an open hole in the graph. There is no vertical asymptote there. And you can actually find the exact limit. You can tell me what that value is here along the y-axis. It's not -8, but you can tell me what that is exactly analytically. That's a cool problem for tomorrow morning when class begins. Great. I think that's good, Curtis. That's a lot tonight.
I learned a lot tonight. I definitely got to check my homework, and that was the best part. Seeing that I got a couple of them right. I haven't forgotten everything from my calculus courses, which is good. So I have a couple of things. Just to thank you guys, everyone who stuck around for the overtime problems. I really appreciate that. We will be sharing those tomorrow morning, I think,
Yes, sir.
as part of the teacher solutions. So as soon as I have those, I'll be posting those up on this YouTube channel link in the description below, so you can go and find that. No, you don't have to rewatch the entire video to get that. Secondly, as always, we have teacher professional development 1-hour blocks, certificates that you can get. If you email me, my email address is in the chat box right now, or will be as soon as the lag is there, curtis@ti.com. So curtis@ti.com is my email address. Use that to send me a request for the PD, and I will send you a link to generate a certificate for tonight's session. So really hope that you all enjoyed it. Thank you, students, for being here, and teachers, I would highly encourage you guys to go ahead and make a note to go look for the student document in the next week or two. We'll have that up there for you for the October, what is it, 2nd? I think is the next one of these that we have. So October 2nd. We'll have the student document up there so you can use that with your students. and then log in and check out the solutions and any questions that you may have. So thanks again for joining us, and we'll see you in a couple of weeks.